let's look at this problem that is actually part of worksheet 7 and problem 4, question 4 in your worksheets. Okay, so this one says that I have a sphere of radius a, and on the surface, on the boundary over here of the sphere, on the surface, it is given a specific potential that is V0 cosine 4, cosine to the power 4 of theta. So the question is to find the potential in terms of the multiple expansion of up to the 3 leading terms, so the first 3 leading terms in the QLM expansion. And to find the total charge, so if I have a potential of this specific expression over here, what is the total charge that creates this potential? Well, so that's what it's asking for in part B. And part C, what is the dipole moments? So what are the Q1Ms over here? So AKA the dipole moments of this specific setup. All right. So this is of a similar strategy to all these multiple problems. The key expression you want is this formula for the potential. So we know that, especially on the outside, the potential can have a multiple expansion of that looks like this. So it's 1 over 4 pi epsilon naught, and have a series, have an infinite series of 4 pi over 2L plus 1, QLMs over RL plus 1, YLMs. Yep, that's it. So that is the general case. So here you have the angular part of the series and of the expression, and here you have the radial part of it. And this is outside because, as you can see, when R goes to infinity, this vanishes as it should be for the potential, so that it is well defined. So the spherical harmonics is, in some sense, is a spherical harmonic expansion, but with a specific coefficient, specific radial part that is expressed like this. Okay, so this is in general. So what we want to do is we want to see specifically what is the potential. Some on the outside, what is the potential, and what are the 3 leading terms of this infinite series? Well, the only condition we're given is that the radius is a, and on this surface, on r equals to a, the potential looks like this. So we want to somehow make use of this information over here. How can we make use of it? The best way to do it is by matching. Okay? So what we do is we want to match the potential at phi equals to a. So on the one hand, we have, on the one hand, this will look like this. So all I have to do is replace the r with a. And on the other hand, this should look like this. So now we want to match this with this side. So here's a nice little trick, is for simplicity's sake, I know ultimately we want to find the QLMs. Well, ultimately actually we want to find the full phi over here, the full scalar potential. However, now I've transformed the problem. If I know all the QLMs, I'm done, right? Because we know exactly what the YLMs are. We know exactly what the spherical harmonics are. So if I know the QLMs as well, the problem is solved. Of course, this is an infinite series, so the problem only asks for the first 3 leading terms over here. Okay, so the question is, how do I find these? Well, we can now project this out by multiplying the YLM conjugate. But before we do all that, we can be a little bit smart because we know that the YLMs, the spherical harmonics, forms a complete basis. If it is a basis, that means they're linearly independent. If they're linearly independent, that means if I can somehow write this in terms of a spherical harmonic expansion as well, I can just do compare coefficients. So that's what we're going to do. But before we even do that, so now the strategy is basically expressing cosine 4 theta in terms of YLMs, a series of YLMs like this. But even before we do that, what we can do is sort of rewrite this a little bit more concisely. C as a big coefficient, C for concise, like this. Okay, so this is just, I'm just grouping all these together into C. So once I compare my coefficients, once I write my cosine in terms of YLMs, I can immediately extract out what the C's are, and then C is just 1 over 4 pi epsilon naught 4 pi over 2L plus 1, QLM over AL plus 1, and then I can invert this and find the QL. Yeah. So I've shifted my problem to find the C's, CLMs instead of QLMs, like that. Okay. Ultimately, we want the QLMs, which we'll plug back into here. Okay, so now we focus our strategy into finding the spherical expansion for cosine. Okay, so first of all, this is to the fourth power, and that means we would expect we need something like the L equals to 4 spherical harmonic. So we can look that up. So the YLM for this is 9 over 4 pi square root 1 over 8, 35 cosine 4 theta minus 30 cosine square theta plus 3. So what I like to do, as I mentioned before, I would like to first get rid of this big coefficient. So it's 8 times 4 pi over 9 y40 equals to 35 cosine 4 theta minus 30 cosine square theta plus 3, like that. Okay, and now I will need to cancel out this. So if I can make this the subject, I can isolate cosine 4 to one side, but still I'll need to cancel out these. So I'll expect to find, I'll need to find out what y20 is. And also I'll need to cancel out the 3, which is the constant term. I'll need to find out what that is. So this is pretty standard procedure. And now you can rewrite it. I'll just directly write out the answer. Okay, so that is basically the spherical harmonic expansion for cosine to the power of 4, cosine theta to the power of 4. Okay, so we also have a V0 over here. So now we're ready to compare the coefficients, right? So let's write it out more clearly. On the left-hand side, we have this situation. And on the right-hand side, we have CLM, YLM, this over here. So now I can just directly compare coefficients. And I will know that C0 is basically, because of the linear independence of these spaces, these spherical harmonics, it's basically V0 8 over 35 times 7 over 8 times 4 pi. So by comparing coefficients, I can extract this out. Similarly, we can do it for C20 and C40. So C20 is going to be V0 8 over 35, 4 pi over 5, 10 over 4, and this is simplified. And finally, the 40 term, which is the coefficient of this side, is 8 over 35, and just 4 pi over that, like that. So that gives us the C0s. And what we want is the QLMs, right? So we know that we will have a Q40, Q20, and Q00. So let's look back at what was the result. What did we simplify for that? So this is actually me simplifying this 4 pi over 2L plus 1, QLM over AL plus 1. Okay, so that was how I defined CLM. So that means QLM is 4 pi epsilon naught to L plus 1 over 4 pi. I know things cancel out, but we'll do that bit by bit. And AL plus 1 right, of CLM. Okay, so Q00, Q0 is basically this. So we'll have L equals to 0, which means this is just 1 over 4 pi. And this is just A, and CLM. So we'll plug this mess in here. Okay, I'll try to simplify part of it. So this is 1 over 5. So this is the C0 term. Okay, so that can be simplified. Further, the 4 pi will cancel, etc. Just to give you the general idea. The next one will be now L equals to 2. So I'll have 5 over 4 pi and A to the power of 3. And we will plug in the corresponding C20 over here. And finally, this is 4 pi epsilon naught. L equals to 4. So I'll have 9 over 4 pi over here. And A to the power of 5, and plug in whatever the C40 is over here. So that will give me all the Qs. And basically, we are done. We just have to package the things up together. So we're asking for the phi for up to the 3 leading terms. So all you have to do is to plug these things in here, simplify these, the rest is algebra, and you will get your phi. And there is exactly 3 terms. So that's good. It's actually a finite series over here. So it terminates with y0, y2, and y4. Okay, so you can express that out for part A. Part B, all you have to do is notice that Q0 is proportional to the total charge, like that. So the total charge is just 1 over square root of 4 pi times whatever the resultant simplification of that is. And finally, to find the dipole moments, we're asking for total charge and the dipole moments. And since we don't have any L equals to 1 term, that means there's no dipole moment. That means all the 1m terms are going to be 0. And that is reflected by the fact that if you plot this potential out, it is a symmetric situation. So you have more, so you have as equal amount of positive charge on top and bottom. That means there's a nice axial symmetry that doesn't give rise to any dipoles. So dipole-like effect over here. Okay, so hope that gives you a sketch idea, and I'll leave it up to your exercise to fill in all the algebra steps.